Okay, hello everyone, and welcome to today's lecture where we will be talking about filters, digital linear time invariant filters, and equalizers in JUICE. And these are the sort of filters one can use in creating an audio effect plugin. First, let me go ahead and define equalization. It's the boosting or cutting of certain frequency components in a signal. It's called equalization because in the early days, transmission over long distance involved attenuation, particularly of the low frequencies. And so this needs to be compensated for so that the spectrum of the output is as much as possible equal to the original spectrum of the input before traveling over the transmission line. And that's the goal here is um, often to obtain a flat frequency response. But now it's been extended and it's really any form of modifying and shaping the frequency response in a signal. So I'm going to review a few of the mathematical concepts here, but it's really just to remind people who've taken digital signal processing what aspects of DSP are most useful to understand filters. It's not all necessary to understand things like today's lecture. First, signals can be represented, filters can be represented in many different ways. The signal that acts on, the system that acts on a signal can be represented as a difference equation, time domain, where the current output is, for a linear system, some function of previous outputs and current and previous inputs. It can also be equivalently represented in the frequency domain via what's known as a transfer function. So essentially for all possible frequencies in the signal, how are they modified in terms of amplitude and phase when being passed through the system? Equivalently, you can represent either difference equation or transfer function as a block diagram, and you can also write it as a simple algorithm. You can do these things easily for simple first order difference equations and so on, but it generalizes to filters with any number of coefficients. So for instance, where the current output is a function of hundreds of previous inputs, or current and previous inputs, and hundreds of previous outputs. Um, there are plenty of uses of high order FIR filters. FIR means finite impulse response, so there's no feedback, and that includes reverb, where models of reverberation might have hundreds or even thousands of filter coefficients, but it's all feed forward. Generally, people don't or rarely design very high order infinite impulse response filters, the ones with feedback, because those are more likely to have issues with boundedness and stability. FIR, which I was just discussing, involves a weighted sum of the last inputs to produce the output, but the output is not dependent on previous outputs. So by definition, it's always stable. IIR filters, then the current output depends on previous outputs, like delay with feedback. Stability then depends on these weights, the coefficients associated with each previous output, and it can sometimes be complicated to determine if they are stable, but one should generally take care to produce stable filters. What do we want in a filter? There's multiple uses, a huge number of uses of filters when working with audio, but generally there are two conflicting priorities. So when we want a cutoff, we want it to be sharp. if one is dealing with aliasing issues where there are high frequency components in a signal sampled at a certain rate, can alias back and appear as audible lower frequency components simply because the way in which the audio is represented can't distinguish between the two. That's something we don't want. And so there we would like a filter that completely, or as much as possible, removes these high frequency components. But um, there are times when we're not that interested in a sharp cutoff. We, we want to, say, boost the mid-range. And we don't want our frequencies suddenly to go from no content to huge amount of content as we go from, say, just under 600 hertz to just above 600 hertz in the frequency domain. We'd like a smoother transition. So when shaping the frequency spectrum and not concerned about an artifact like aliasing, then one generally wants a smooth rather than a sharp filter. With both cases, of course, it can depend, but usually when people are doing things like equalization, a lower order smooth filter is perfectly fine. You can get these sorts of things with IIR filters. They are certainly computationally efficient because to get a decent quality behavior, you only need a small number of delays. However, FIR filters, as mentioned, are always stable and are generally linear phase. Linear phase means that the phase is exactly a linear function of frequency, which means you can predict what the behavior does to phase, which means that the filters have less coloration, unintentional shaping of the signal. Sometimes we do want high order filters, high order IIR filters. They can generally be made two ways. Well, they can be made many ways, but sometimes people have small lower order sections, like first and second order sections of the filter in series. So it goes through some low order frequency shaping, then mid range, then high range, and so on. Or it does them all in parallel, so it breaks the signal up into three copies, passes them through a filter that shapes the low frequency content, another shaping the high frequency content, another for the mid-range, and then sums them all back together, where simply one needs to make sure that the summing them all back together is not just increasing the amount in every frequency band that is not being intentionally modified. So series and parallel implementations are possible, and you will find both in frequent use. So we talked about general properties of filters. We haven't gone through the main filters that are used with audio. And if you've studied digital signal processing, you will recognize many of them, but not necessarily all of them. There are some filters that just aren't typically covered in a standard DSP textbook, but are still quite important with audio. First, we have low-pass filters. Those are the ones that try to keep the low-frequency content, but remove all of the high-frequency content. Similar to them, we have what's known as a low shelving filter. That's one that isn't usually covered in DSP. Low shelving filters try to adjust the strength of the low frequencies, applying some gain that might be greater than or less than 1. So it's creating a shelf, and rather than removing all of the high frequencies, it simply leaves the high frequency content unchanged, unaffected. We then have the equivalent for high pass. So high pass filters are ones that try to remove all the low frequencies, keep the high frequencies unchanged, whereas a high shelving filter provides a shelf, a boost or a cut to the high frequencies and tries to leave the low frequencies unchanged. It's a simple mapping from low pass to low shelf or high pass to high shelf. But the real question is the frequencies you don't care about, do you remove them or you just leave them unchanged? And we then also have what's known as band pass and band stop filters. These are ones where rather than focusing on the low frequencies or the high frequencies, you focus on some mid-range. And the question is, do you want to keep that mid-range and remove everything else? Or do you want to remove that mid-range and keep everything else? Um, those are sort of extreme situations of the peaking filter where the peaking filter can apply a boost or a cut. So when it's applying a boost, the extreme situation is a band pass. When it's applying a cut, the extreme situation is a band stop. But the idea with the peaking filter is it leaves everything outside of the region unchanged, but it applies some attenuation. It may not be maximal attenuation, or some boost may not be the maximum amount, to the frequencies of interest. So in the plots that were just shown, those are all sort of the ideal exaggerated behavior where, for instance, it's perfectly keeping all the low frequencies and then suddenly removing all the high frequencies. Much more common is smoother filter designs where there's a region of transition, and it can be a very slow transition from the response at high frequencies to low frequencies. So here we are showing low shelving filters and high shelving filters, and we're showing the effect of changing the gain, so more boost or cut, and also changing the center frequency, so at which point it makes the boost or cut. We could show the same thing for the peaking filters, only now we're looking at some mid-range. And so we can vary the gain, we can vary the center frequency, and there's one more parameter for the peaking ones, the bandwidth. So do we have a very narrow region that we're interested in, or a very wide region that we're interested in? Notice there's what's known as warping. So it's best seen when varying the center frequency here. Look at this curve where the peak value is around 0.15, maybe close to 0.2, but it very sharply goes up and very slowly goes in the other direction. And you see it loses its symmetry more and more when the center frequency is far from the mid-range of possible frequencies. Okay, often filters are defined not in terms of bandwidth, but in terms of Q, which is the ratio of center frequency to bandwidth. So this has a benefit. First off, in many cases, it's more intuitive. High quality means sharper filter, low quality means more spread, and one can talk about constant Q filters where it has the same sort of behavior, whether low frequencies or high frequencies, but because so many things are on a logarithmic scale, it needs to sort of adjust what it's doing as you go from low to high frequencies. And constant Q does that. On filters are generally not symmetric when you go far away from the mid-range. That's this warping. But on a log frequency scale, they can appear symmetric. High order filters give the sharper and sharper ones, where you get closer to that extreme ideal behavior, like a bandpass filter that is exactly 0 and then jumps up to being exactly 1. and then back down again. Now you need to go to very high order filters to get anywhere close to perfect behavior, but it is true that the higher the order, the sharper the transition. Implementation. Let's just consider a filter, simple filter. It has three coefficients defining the feed forward and two coefficients defining the feedback path. So feed forward is the dependence on current and previous inputs. Feedback is just the dependence on previous outputs. So often you will see something where there's one less coefficient for feedback because current output obviously is not dependent on current output. What do we need to calculate this? Well, one approach could be that we have a function that takes one new value of x of n and returns one new value of y of n. So like this, we keep a1, a2, we keep these coefficients, maybe they are initialized somewhere. We have a function that has some output y. How do we make y dependent on the input x? Well, it comes straight from implementing that equation, explicitly the way it looks. But we need to keep track of x of n, and one previous x, two previous x's, and one previous y, and two previous y's. So y now is b0 times x plus b1 times x previous, and so on. And then after we do this, we need to shift all of our y's and x's. And that's what's done here. The new value, for instance, of x previous is what was currently x. And the new value of x twice previous is what is currently x previous, and so on. We shift everything. I'm going to show this, but I'm not going to go into detail on it. So here was the form of a filter in the time domain. If we go back to the very first couple of slides, here we can similarly express this as a transfer function in the frequency domain. So for our low pass, high pass, slow shelf, high shelf, band pass, band stop, peaking filters, what is the transfer function for the lowest possible order for each of those filters? And it can be calculated, it can be derived. Here they are. So a low pass filter, you have the center frequency expressed in a range from say 0 to pi, I think it is, for omega c. And the low pass filter only depends on that one parameter for the lowest order, which is first order. High pass similarly only depends on omega c, so that cutoff or transition frequency. When we have a low shelf, we have the gain associated with the shelf G and its center frequency or cutoff frequency. When we have peaking filters, skip down, that depends on the gain, so the height of the peak, the bandwidth, how widely dispersed it is around that peak, and omega c, at which frequency the peak is located. So, let's see. This is basically induced with some slight variations, but very similar filters in JUICE for low pass, high pass, band pass, etc. There's also all pass filters, which I believe I discuss in another lecture, and notch filters as well. So there's a structure for the coefficients and a class for filter that uses that structure. JUICE has many ways to implement filters, IIR filters. And it's not that hard, and certainly not that different to implement things directly versus using Juice's built-in commands to do so. So it's not, there isn't a huge benefit to using the Juice IIR filter class. But one can first off do things directly. One can use the filter class where coefficients are saved somewhere. Or one can use the filter class and make peaking filter, which is another class that specifies how a filter must look based on, well, based on these sorts of equations for the coefficients of the filter for different behavior. Let's go ahead and look at the middle one where we're using the Juice IIR filter class. We first specify the parameters on the interface. We add parameters for center frequency, gain, and Q for the interface. And we add the filters that we will need for each channel in Prepare to Play. Then in the process block, we define the variables. So we get the gain, the Q, the center frequency. From center frequency and knowledge of the sample rate, we can get a normalized value for the frequency. And we can basically calculate the parameters, the filter coefficients, from the formulas given here. So for instance, if we have a low shelving filter, what would be the coefficients? What is the square root of g plus g tangent omega c, the normalized frequency, over 2, and so on. And we have a few lines of math to get all of those coefficients. Then we can just use this set coefficients method. That's all part of the Juice IIR filter class. And we can process the samples again based on that class. So this is still fairly simple, and it's not the optimal solution. It recalculates the filters every single block. We certainly don't need to do that unless coefficients have been changed. It only implements peaking filters, so we could have a bit more math for all the possible types of filters, and it doesn't chain the filters yet. But it's not a huge amount of extra effort. Let's see. Yeah. So I'm going to give an example right now. Like I said, it's not a huge amount of extra effort compared to implementing the filter entirely directly. But let's go ahead and see. So I have our tester, which is connected to the filter, which then goes into the output. So let me start with a gain, and this is a decibel gain. Oh, yeah, okay. So very close to a gain of 1. Um, so this is the normal output. I have a filter being applied, but it's only a very small attenuation. And let me put the center frequency, because the frequency itself is around 1 kilohertz. So that's close enough. So now I have a peaking filter that attenuates the signal. And yep, I should hear the signal going down around 40 decibels. Not quite, because I'm a bit off here. There we go. But yeah, there's still some signal left. I can similarly boost it. If, on the other hand, I was away from that frequency, it shouldn't change it much. Okay. And yeah, I can still hear most of the signal there. And if I make it a sharper one, it really shouldn't affect the signal. whereas it might still affect it a little bit if I make it a very slowly changing, yeah, not sharp. And I can also do these tests with a noise signal. This is going to sound pretty horrible, but I'm going to apply a boost at a particular frequency, and I can slide that center frequency. And that is it. So, thank you all very much, and see you next time.